introduce Tim Kraska, who's going to talk to us about the case for learned index structure.
Thanks for having me here. So I'm going to talk about some work I did at Google, and now we are heavily continuing with that. Actually, Google is supporting our research now very heavily because I think it's quite some exciting work. The basic idea is we are exploring how we can use machine learning models to enhance and sometimes even replace traditional index structures, algorithms, data structures in general. So when we published the technical report on that, you might have seen a certain wave in the social media coming on. Just by show of hands, how many of you have heard about the paper before? Okay, quite a few. So it all started with this tweet by Christopher Manning, machine learning just 8 algorithms in 1 large byte. I just want to give you a disclaimer up front. By no means I'm claiming that machine learning just had 8 algorithms and data structure and that it will subsume it. It was not going to happen. But I think our work shows that it took a small delicious bite from it, and that's still a very interesting research direction for a lot of future work to come. So why were people so excited about it? That's mainly because all systems, all applications are built from fundamental building blocks like the data structures and algorithms we know from CS 101, like sorting algorithms, hash maps, different types of trees, and so on. Those data structures have been developed essentially since the 80s, and they all are designed that they make no assumptions about the data. Right? So they have this really nice worst-case guarantees we love, but at the same time, they might not be optimal in the specific case for a user. So let's take a look at an example. Let's assume we want to index all the integers from 900 to 800 million. Right? And we want to index them so that we can do range lookups. Right? That's the reason why we have them sorted in the first place. On one hand, we could now use a B-tree for that, which has a storage complexity of O of n, and every lookup costs us log n. Or, because we know that we stored all the integers in this array, we could use the key itself, the lookup key, minus 900, to get an offset inside this array and look it up directly. Right? So it's just this is definitely better for this particular case. Now we have a lookup of O of 1, and the storage complexity also of O of 1. It's just this function we have. This also works now, let's say, if we have every other integers, every even integers from 900 to 800 million. In this case, we still have the lookup key minus 900 divided by 2, and we get again an offset inside the array, which gives us a starting position now to do a range scan from that. This also is true for other data distributions and patterns. You can generalize it. As long as you find certain patterns in the data, there's a potential to take advantage of them. So essentially, we took the black box, that the data structure doesn't have any knowledge about the data itself it's indexing, and make it a white box. And in certain scenarios, not in all of them, of course, but in certain scenarios, we can get significant gains because we take advantage of how the data is actually structured and looks like. Now, obviously, it would be very inefficient to design a data structure or a system in general for every specific use case and every specific customer or user. Right? This is simply not feasible. But here's where machine learning can come in, because with machine learning, maybe there's a chance to automatically discover these patterns so that we can take advantage of them. So let's make it a little bit more concrete with a B-tree as an example. For the moment, just focus on an in-memory, immutable B-tree. There are no inserts, no paging. I will cover them later on. What a B-tree does is, given a key, it finds the position of the page where this key might be contained. Right? So now I said, OK, everything should be stored in a continuous region in memory. So what a B-tree does is, given a key, it finds you the position inside the sorted array. Right? And then we know if the key exists, it should be from this position on plus the page size. This is what we still have to search. So we do a final search in this area. In that sense, a B-tree is already a model, because given a key, it predicts me the position inside the sorted array, and I have an error around it. In the normal B-tree case, the error is defined by the page size, because we only index certain keys from the page, not every single key. Now I can replace it with any other type of model, right? Just given a key, predict me the position inside the sorted array. So you might wonder, OK, how do I get the strong error guarantees? On one hand, it's surprisingly simple, because you don't care about generalization. You care about the data you have. Meaning, you only need to know the error for the data you have stored in your database system. And one way to calculate it is you execute the model over every single key you have in your database system and see how far you're off. And then you memorize the maximum under or overestimation. This gives you an error bound. right? On the other hand, this is not even needed because everything is sorted. You can easily correct it. So it's not even needed that, and actually now we take advantage of that. Furthermore, it turns out what you're doing in a B-tree is nothing else than predicting the CDF of the data distribution. So another view on the problem is if you want to find the start point of a key in a sorted array, it's nothing else than looking into how much probability mass is there for any key which is like either below or equal to the key you're looking up. So it's f of key times the numbers of keys gives you then the position inside the sorted array. If this model, the CDF model over the empirical data distribution would be perfect, every single estimate would just give us the perfect position. So B-trees, in that sense, already do that. And in machine learning terminology, you could consider a B-tree nothing else than a regression tree. And it's just like a form to make that prediction, which is just like, OK, if you take that now all together, what does it actually mean? And I have pretty good news for this community. It's like database people were the very first to do large-scale machine learning. Right? You should all be very proud of that and also bring that out to the world. Right? We were first, it's proven now. So, but nevertheless, we have B-trees, but maybe we want to use other models as well. And we can use maybe linear regression models, multivariate regression models, even neural nets. It's quite open now what we can do as long as we try to estimate the CDF. And the hope is that by using other types of models, that we hopefully get significant advantages. First of all, we hope that maybe we get a smaller index. I showed you already the case of the array. If you can take advantage of this pattern, maybe you get big benefits out of it. There's also hope for faster lookups. Again, the array functions an example here, because now something which is log n, you always have to traverse. Maybe you don't need to do that anymore. Maybe there's a hope for more parallelism. This is mainly because if you think about how you find something in a B-tree, it's determined by a lot of if statements. Traversing a B-tree is nothing else than doing if statements all over, right? For the sort of every page, for jumping down, and so on. Now we can potentially replace it with mainly additions and multiplications, which are much more easily to parallelize. And even better, there's potential to put them on TPUs and GPUs. Much easier than in other areas. There's also hope that inserts might become faster, and hopefully I have some time later on to talk about that. So this sounded like an interesting idea to try out, so we tried it out. We used TensorFlow as like a starting point. We wanted to index 200 million web server log records. We wanted to index the timestamp. We tried like a 2-layer neural net for it. The prediction task was, given the timestamp, try to find me the position inside the sorted array. So we compared it against a cache-optimized B-tree, which roughly took like 250 nanoseconds. What's your guess for how long TensorFlow took? Any guesses? 100? No. 80,000 nanoseconds. So the first attempt, we just managed to make it 3 orders of magnitude slower. Right? Great success, very encouraging. Then we started to look into what can we actually do and why is it happening. On one hand, TensorFlow is not designed to run in nanoseconds. Right? It's designed to run larger models like language translation. And normally they target milli or microseconds, but not nanoseconds. So there's a lot of overhead for executing these larger models more efficiently. Second, often we get like actually a better prediction where the key might be, but we might not actually take advantage of it. Right? So for example, if you predict something which is right next to the actual key, we still searched in the whole like min and max error region which we determined beforehand. Right? So there's potential to take advantage of the search space. There's like the B-tree is very cache efficient because it keeps like the top nodes inside the cache automatically. So like we are up to something which is highly cache optimized. And decision trees or B-trees, they are really, really great in overfitting. Right? So like they are really good. If you ever did like some machine learning models, like decision trees, you can perfectly overfit a lot of stuff with if you make it deep enough. And overfitting in our case is often a good thing because that means on how well you fit your empirical data you have, the data you are stored. Because we are, as said before, if you disregard inserts, we are less about generalization in this case. So we started to address the different problems, one after another. So for the first one, we implemented a code synthesis strategy. So like we don't use TensorFlow anymore. Instead, like you train the model with TensorFlow, but then you generate code out of it to avoid all the overhead. We developed a different bunch of search strategies. Both of them are more in the paper. Here, I only want to cover on how we address the last two, because I consider it's a key contribution of our paper. So how do we get the precision down? And one contribution we make is just like it's actually borrowed for something in the machine learning community called mixtures of experts. So on how we try to, like with the least numbers of operations, to get to a good position estimate is by, we train first a model over the entire data. This model makes a prediction where the key might be. And based on this prediction, we pick another model, which hopefully then makes it like an expert for a certain region of the space, which then hopefully makes a better prediction for the next step. And this might be, again, makes a prediction which picks yet again another model. Okay. So it's important to point out this doesn't have to be a tree. This is more a graph because two experts on one layer can pick the same expert on the bottom layer, right? So it's just like it's a graph structure. You can train that in different ways. The algorithm is in the paper. Similar interesting is that you can mix and match models for the different types. So you don't need to use the same model throughout. Maybe something else works better at the top, whereas at the bottom. You could also use B-trees for pieces where you think the model is not good at all. Right? So by doing that, if you just say, like, OK, if a part of this range doesn't work well, I replace this with a B-tree because this overfits very well, actually you can bound the worst-case performance to the one of a B-tree. If the error is not good, it all falls back to a B-tree. And that's just the way on how you get like, the worst-case lookup performance, very similar to a B-tree. Does it have to be neural nets? By no means. Right? Actually, whatever you can use to build this function, key to position, is fair game. And you should play around with it. We tried a whole bunch of like very simple shallow neural nets, as well as linear regression, multivariate regression, different types of feature engineering. And it's all fair game on how you combine them to make the predictions to get like from this key to the position inside the sorted array to replace a B-tree. So does it work? Here's showing results for like 200 million records of map data. We have other data sets in the paper. As a comparison, I used like the B-tree which we had before. It's a cache-optimized B-tree, dense, meaning there's no free space in the page, in the different nodes of the tree. The lookup time is like 260 nanoseconds at like a size of 30 megabytes. We used this particular setting because it gave us the best performance. As a comparison, learned indexes for different sizes of the second stage, so meaning how many models we used on the second stage, gives you a different trade-offs between lookup time versus space. And what we can see is like that we can get 60% faster at the 20th of the space, or we could get 70% faster and save 2 orders of magnitude in like index size. So they are pretty encouraging. Now you might have seen some blog posts, like for the ones of you, and you might be wondering, like, what about those? Actually, the blog post had some issues because like they were not under the like same hardware platform. They didn't use like the payload we were using. It was more like an apples to oranges comparison. But by then, now we try to do the same thing on our platform again. Here, I just show one result. It's comparing learned index structures in regard to lookup time and size. So lower left corner is better. Against other data structures out there. For example, FAST is a highly SIMD-optimized data structure. It's pretty large. Fixed-size read-optimized B2 with interpolation that was proposed in the blog post. Lookup tables, this is a succinct data structure we also tried out. And you have learned indexes there. So it looks pretty encouraging, at least, if you compare it in the same environment. And just like it's important to point out here that by no means I'm saying learned indexes will always win. This highly, highly depends on the data you have. This data set also has like large pieces which are pretty linear, therefore this like model fitting works extremely well, right? But like it just depends, and the nice thing is, in the worst case, we fall back to the B-tree implementation. So what about our assumptions, like updates and inserts and paging? Actually, we have a paper on inserts and updates yet. It works a little bit different, but we're heavily working on that, and I can talk more about it. Paging, turns out, you need to actually do something in addition. If you just take Postgres and you want to do learned indexes, then it probably wouldn't work. But if you determine the paging strategy based on the index, like almost like using it as an index organized table, you can make it work. Hopefully, I can tell you, like, if you want to know more about it, just ask later on. So we started with B-trees. But the similar idea actually also extends to other data structures. And we are very, very excited about that. For example, you can improve hash maps potentially with that. The core problem with hash maps is often that you have conflicts, meaning different keys are mapped by the hash function to the same slot. Right? And then you need to deal with them. maybe you can use a model, and it turns out to be the same CDF model as before, to avoid some of the conflicts. If you would have the perfect CDF functions, and you learn it perfectly, you wouldn't have any conflicts even. Right? So you can reduce some conflicts, and we show over several data sets that we can actually reduce the numbers of conflicts by creating such a hash function. Right? In this map data set, actually the savings are up to 75%. So this reduces like the conflicts quite significantly. Yet again, you might have seen a certain blog post, right? But what the blog post got like significantly wrong is we are not replacing the hash map architecture. We are only building a better hash function. You can think of a different way to build a perfect hash function, just like using a continuous model. And you can use it with different hash map architectures, for example, with cookie hashing, separate chaining, or whatever else you want to come up with. Right? So we have results on that. For example, we compared against the Stanford hash function, the commercial cookie hash function, and we have our own one. And of course, depending on your hash map architecture, as well as your payload and other properties, you get different results. Again, by no means I'm saying this is always the best thing to do. It just depends. Right? And it provides you a new way to think about on how you create such the hash function and take advantage of that. OK, so there are a lot of other data structures out there, and we are heavily working on them, as well as like I know that other researchers now started to work on them as well. In the paper, we also cover Bloom filters. One of my colleagues is now working on scheduling. There's an interesting work around similar ideas about cache policies. It's actually quite exciting. What I want to ask you here is, let's assume you have an oracle which tells you the CDF of your empirical data distribution, meaning the data you have stored. How would you design your current algorithms, data structure you're working on differently? Right? And the power here partially comes from the fact that we use continuous functions. Furthermore, if you use a model for that, what you get for it is just like actually the model learns, adapts to the data of this particular instance of your application. Right? And this is like where some of the power is actually coming from. There's a huge potential for having this, then deploying it on modern hardware, because it changes the type of computation you are actually doing. There's also, in some cases, chances to lower the complexity class in certain scenarios. Again, it highly depends on the particular case. It's all about finding patterns. And this what we saw like in the data array case as before. Again, a warning up front, this is not an almighty solution. Right? It just depends on the cases, and I think there's still a lot to be research to be done to make it fully practical. We understand now more and more than we had even when we published the technical report. Now we are much further ahead, and there's a lot of excitement at many different companies I'm happy to talk about. In that context, I also would like to announce a new lab we are currently building at MIT called DCell. It's around the topic of doing data systems for AI or using AI for data systems, and there are a bunch of people involved. And with that, I conclude. I'm very happy here to be here and excited about this new direction. And I also would especially thank my co-authors, Alex Beudel, Etchi, Jeff Dean, and Elkus, for helping with this like whole paper and the whole process. It was a great time I had at Google. If you ever get the chance to do a sabbatical at Google, I highly recommend it. Thank you.
So I've seen that this technique could be also applied to sorting. So my question is, could we possibly even learn monotone hashing functions?
Potentially.
Okay.
Any index building require a building time, also a maintenance time if you want to support updates. What is the overhead in this case? You're training a model. How long you're going to train it?
Right. So it highly depends what type of model you are using. So we try different types of models, like the often simpler models in the IMI structure work the best. For example, a multivariate regression model, you can actually train in one pass over the data. You don't even need the full pass over the data. You can work it on a sample. And this is extremely fast. Yes. Right? So it just depends. An N model, of course, takes longer, and you have to train it differently. But again, sampling might be a good strategy here. And there's a fundamental thing, again, between the population CDF and empirical CDF, which goes much further than that. But it's not necessarily that bad. It depends.
Right. Wonderful. Thanks.
One more question.
I have two. Can I say? Okay, first question is about your example. So the first one, the simple example that you can data is linear, like integer go up. If it's statistical data and if it's a columnar, would it be more efficient to simply use a compression, use that formula? So you don't need to even go look at the data.
So in all the different cases, I'm not sure what you mean by compression, because compression is normally orthogonal, but in all the cases, often if you look hard at the problem, you can come up with something which works better in this particular case. The main insight here is that we can automate the process. Right? So it's just like if you have now every integer, it's like the same mechanism, the same inner structure we use as if you have every other integer. You don't have an expert which tunes that manually.
But then the machine learning actually, when you have the new data, you have to relearn, right? So
not necessarily. So for new data, it's actually pretty interesting. So let's assume, I even have a slide on that. So for new data, let's for a second assume you only have appends. Right? So let's assume that your new data, the appends, come in with the same pattern, similar pattern than the data you already have. In that case, you don't need to retrain your model, because your model extends to what's coming new, right? So whereas in a B-tree case, you have to rebalance the tree constantly with all the new data which is coming in, now your model actually generalizes, hopefully, to the new data, right? In this case, actually generalization starts to play out, right?
Okay, thank you. And then the second one.
I think I need to cut you off because we're...
Thank you.
The next talk is titled Dostoevsky